Okay, before I go further, let me just point out a few things. First of all, finding a neighborhood around a vertex Vi defined by a radius Ri can certainly be done also for general networks. What do? You place yourself, you position yourself at vertex Vi, and from vertex Vi, along all possible paths emanating from Vi, you just go a distance of Ri units, which means you're pulling a string of length that much along all possible paths. The only difference from tree networks is there are too many paths to consider. Nevertheless, it's doable. Okay? And the output will be a subnetwork. And that's going to be connected for sure. And, thank you. Teşekkürler. It's going to be connected for sure. But when you start intersecting a pair of such neighborhoods in a general network, the output may not be a single piece connected subnetwork. It may actually split into different connected parts. That will not occur in the tree network case because you can see actually in the composite neighborhood representation, it's a center plus a radius, which gives you the representation, which is a subtree. It's a single piece. That's why everybody or every composite neighborhood comes as a single piece, which means at the end you obtain your entire intersection in quite efficient time or n time. But in a general networks, when things start splitting, you can keep track of them. Nevertheless, then when you start intersecting two neighborhoods, you should try to intersect every piece of that neighborhood with every piece of the other neighborhood, which gives you time proportionate to the number of pieces you have, the time proportionate to the square of the number of pieces you have. And that may actually start exploding as you go along. So even though things are doable, they may not be that efficient. Okay, now I'm going to continue with this. Let's erase this pictorial part. Sure. It can be a big question too, no problem. Yes.
When we select a vertex Vi and we should find a pair of neighborhood with that, does that neighborhood has to be the smallest distance between vertex Vi, or can it be any neighborhood for the beginning?
Are you asking for a single neighborhood, yes. Vi and Ri? So for Vi and Ri, if you have some kind of a tree network, if you're, for example, here, suppose this distance is 0.5, and you're asking, suppose that's your point A, and you want to compute neighborhood of A with radius, say, 1. Okay? So what you do is, you go .5 distance unit from that point on, so that's one portion. Of course, you also go this way. Again, the length is 0.5. That's another portion. You also go that way, and suppose it extends up to here. So you go in all possible directions from out of that point to all possible paths. Okay? This is more complicated in a general network because you're following a shortest path in a general network, so paths may start switching actually after a while. Okay? What was the last property number that I gave you? Property 7? Okay. So let's state property 8 now. If the intersection of these neighborhoods is non-empty, then the sequential intersection procedure finds a point A in T and a radius R, which is certainly non-negative, such that that last or that neighborhood AR gives you the intersection. This property simply justifies that the algorithm does what it is supposed to do. Okay, that's all. So, if this entire intersection is non-empty, then the algorithm outputs a non-empty intersection, a non-empty composite neighborhood intersection at every execution of the main step of the algorithm. So the final neighborhood that remained in the list gives you A and R, as well as the neighborhood around. So this property actually is concerned with the non-empty intersection case. What happens if the intersection is empty? Does the algorithm do the right job?
You just eliminate the pair and add nothing. Actually add the empty set, and you get a bunch of empty sets in the end.
Right.
The intersection of which is the empty set.
Exactly. So if the intersection is empty, at some point in the algorithm, some pair will give you empty intersection, and that empty intersection will be added to the list as a new neighborhood. And as you continue to intersect, it will start intersecting everybody else, and then finally the output is going to be an empty set. Okay? So I was going to write it here, but you can write that on your own. Okay? Yes?
And the last neighborhoods in the list, which is not neighborhood, implies anything. For example,
In the empty case or in the non-empty? In the empty case, it doesn't really imply anything.
for example, I thought that it may imply that some extension of some parts may provide a neighborhood.
Well, it implies the following. There's at least one pair of neighborhoods that do not intersect. Okay, that's what it implies, which means that there's at least one pair of vertices I and j such that the distance between I and j is greater than, strictly greater than, Ri plus Rj. That's what it implies. There may be more than one such pair, though. In other words, property 6 fails. Okay. The if and only if statements at this one, well, actually, all of them fail in this case. Okay. Let me give you an example. Sometimes you need some numerical examples to relate to what we're doing. So let's assume the tree under consideration is this one. Seven vertices connected in this way. The edge lengths are 2, 3, 5, 4, 4, and 2. And that's my data. Ri are 5, 7, 6, 6, 11, 16, 16. Okay. The order of processing will be first intersect 1 and 2. Then continue with the intersection of the output of this with number 2, number 3, number 4, etc. Okay? Okay. So later you can follow what's going on. And here are the intermediate outputs. Maybe I should draw these things a little bit smaller to fit all of them here. So the first vertex under consideration is V1. And my second one is V2. V1 will have a radius of 5, which means I'm going to attach a string of length 5. So this wiggly line is a string. Just imagine that's a string. That's not part of the tree. Okay? The length here is 2. This one is 3. This one is 5, etc. All right, so what is the intersection with number 2? Number 2 has a string of length 7 from here. So where do you think will the intersection be? Just think of it this way. When you pull this string tight towards here, it will reach here with a remaining length of 3. So just in your head, try to do these computations. And that one also reaches here, so this portion is certainly included. Okay? And then, of course, this 3 is, it becomes a bottleneck relative to the other one. So you pull this tight towards this one, so it actually covers this portion, and you pull it tight this way until you get to a point where the edge is split into 2 parts with 3 and 2. Okay? So that's your first output. What is my A and B, A bar, R bar here? What do you think?
Can we think about parts which is not in tree? For example, can we say that V1 is A and 5 is the radius?
V1 is A.
And 5 is the radius.
So you are saying that that's going to be your A bar, and 5 is? Yes, you can say that. Mm-hmm. In fact, if you look back into the definitions of A bar and R bar, what should it be? That's what I was asking. What case applies here?
Case 2.
Case 2? Case 1. Case 1 applies. Okay? So the output here is from case 1. Are we sure about that? The distance between V1 and V2, let me just check. In case 1, we want this to be true, right? R1, and you want R2 here. That's right. And this distance is 2. R1 is 5. That's 7. Yeah, case 1 certainly applies. Okay? Okay, so that's my first output. Now, what else do we intersect the next one. Let me call this V2 bar. Now I'm going to intersect neighborhood V2 bar, R2 bar with and V3, R3. That's what I'm going to do. V3 is, that's 6. Yes? That's V2 bar. Well, it remains in the tree. It's not in the list, though. Well, the tree does not change, of course. The tree is still the same tree. Only portions of tree have different status now. They are either in or out. Yeah? The cross-hatched parts are in. All right, so we're looking at this with 3. So when you pull this tight towards here, it will reach here with a length of 3. It will reach here. So the intersection here is going to be a new neighborhood whose centers will be this point, which I call V3 bar. So I'm calling the output of this V3 bar. What's the radius? It's going to be 3. Okay? What's the next one? You intersect it with V4, R4. So let's do it here. So what happens after this point on is you get this neighborhood where this point here happens to be your number 4 center, and then it actually continues to be the same center in the remaining iterations. You can do that on your own later, and it turns out that R4, R5, R6, and R7 with bars, they are all equal to 2. So from this point you go 2 units here, 2 units the other ways, and that's your final neighborhood. Okay. Let me ask you this question. Suppose you have some data, RIs, and then you apply this algorithm. You compute a non-empty intersection at the end. So you do have a neighborhood with center A, radius R at the end. Now, suppose I decided to reduce every radius of every vertex by some constant amount, say epsilon. Okay? So the question is, with the new reduced radii, do you have to just work out the algorithm one more time to compute the new neighborhood? Or can you somehow make use of the old neighborhood to directly compute the new neighborhood relative to the reduced radii? Does everybody understand the question? Okay, fine. You have a...
For every end of the last neighborhood by epsilon and shrink the
neighborhood.
Yes.
So what do? We just look at the last neighborhood, shrink it by epsilon, from the endpoints. How did you get to that conclusion? Yes, that's correct, but how did you get that?
Because if there is an end, there is a dominating radius which cuts that, which causes that end, and if it reduces by epsilon, that end also reduces by epsilon.
Okay, yeah, that's the main idea, but we cannot use that as a proof. Yes, first of all, your claim is right. If you reduce everything by epsilon, then the final output is also reduced by epsilon. So first of all, let's write that down. So that's the issue we are addressing right now. Suppose I already computed the composite neighborhood for the intersection of these neighborhoods for given RIs. Assume it's non-empty. Okay. Reduce each Ri by epsilon. Now I need to compute the new intersection with the reduced radii, Ri minus epsilon. And NS says I don't have to reapply the algorithm. All I have to do is to shrink the final output by epsilon, or reduce the radius by epsilon. This is correct. So let's replace the word need by then. This is the new output. And the question is why? He gave a justification, but looks kind of complicated. I need a cleaner justification. For a cleaner justification, let's just look at the definitions we had for the composite neighborhoods. When you reduce, this is for a single pair of intersection. When you reduce your R and R prime at the same time by epsilon, what happens? First of all, the cases do not change because you have an epsilon reduction on both sides. So if case 1 has applied, it will still continue to apply. If case 2 has applied, it will continue to apply. If the otherwise case applied, then it still continues to apply. And so if you take your algorithm SIP and apply it again, however, using the same order of selections from the list as you did in the first time, so you retain the same order. First of all, the A bar will not change at the main execution of the main step of the algorithm. Okay? Does this change? This will not change either, because whatever case applies, well, it will change actually. It will be reduced by epsilon. In this case, it will be reduced again by epsilon, and here it will be reduced twice epsilon, but then you divide it by 2. So again, all it does is, when you apply the algorithm in the same order with reduced radii, you simply reduce the composite neighborhood in each step by epsilon. That's it, without changing your A bars. So the final output will be accordingly this one. Okay? So let's state that as a property. All right, that's a short way of expressing what we discussed, okay? So I'm going to state that as a new property, which is going to be my, which property is that? Property 9, 8, 9? Okay. So if the original intersection is non-empty and given by neighborhood A, R, then neighborhood A, R minus epsilon will give you the new intersection, which is going to be non-empty for epsilon less or equal R. Whatever R you have, you cannot exceed that. Okay? The proof is already given in the Y part. What's the conclusion if your epsilon happens to be a negative number? In that case, when you take epsilon away from R, Ri, actually you're increasing the radii, in which case, of course, the same discussion holds. Nothing changes in that case. So the property also applies for expansions. Yes.
I think you can find some algorithms if some of the radii reduced by epsilon, and what will be the last neighborhood?
We can devise an algorithm to answer that question. So are you referring to the case where you reduce Ri's by different amounts or by the same amount? Or sum of Ri's is reduced by a constant amount. Well, what is the algorithm? If that's a simple algorithm you have in mind, tell me. Otherwise, tell me after class, because I don't want to go into a long discussion. Is it a simple one? Huh? You have to think. Okay, if you come up with a clean algorithm, well-justified algorithm, you let me know. Maybe that will be a new contribution here, okay? Because nobody actually did that before. So property 10. Well, actually, it's not property, but it's a corollary. Okay. Here's an interesting corollary. Put in simple words, it simply says that SIP is order invariant. Meaning that for the same data, if you apply SIP by different choices of orders of vertices, then you will end up with the same output in each case. Not the same neighborhood, but the same A, M, R. So let me make this precise. So if you apply SIP twice with the same data, but with different orders, and if the outputs are NAR and NA cap R cap in the two applications, of course, since we're computing the same intersection, the final outputs as a set or as a neighborhood will be exactly the same. So the note in the parentheses, simply that's a trivial fact. I'm just declaring that. But the more important claim here is that A will be the same as A cap and R will be the same as R cap. So regardless of in which order you apply, you get the same point and the same radius at the end. That's interesting. Okay? Because usually, well, essentially almost all algorithms are dependent on how you select things. When you have optional selections as you go along, things become different. Especially that's quite pronounced in integer programming. That's why certain selections will get you to the optimum quite fast. The other selections will not. Okay? So that's an important property. Always think of if your actually algorithm is order independent or dependent. So let's look at the proof of this.
I was also asking this question at the beginning.
Oh. Yes, you were. And the answer was yes, but how you prove is... Actually, the proof of this in the original paper is very complicated. Well, it's not very complicated, but it's quite complicated. I'll give you a much simpler proof, and we'll see if it will convince all of you. Okay, so how should I?
Is it,
Yes.
This is from like A is equal to A cap and R is equal to R cap, but because we may have the same neighborhood represented with different A's and R's.
You're right. We may have the same neighborhood with different centers, and yeah, let's first answer that because that's a valid point you're making. So here's a remark. Note the fact that A, R equals A cap, R cap does not imply in general that A equals A cap and R equals R cap. Here's a simple example. Just think of your tree being the unit interval from 0 to 1 with vertex, two vertices, one at 0, one at 1. Okay? Now, let me just draw the picture here. So this is 0, this is 1. That's my tree. Now, let me take point A to be 0.25 units from that endpoint and 0.75 here. So if you look at the neighborhood of A with radius 0.25, where do you get? You get this neighborhood where that's the halfway point between them. Okay? But then this will be the same as the neighborhood of vertex 1 or point 1 with radius 0.5. You see? That's your A cap. So A is not the same as A cap. That was the point you were making? Okay. Now let's go into the proof of this in the remaining 5 minutes if we can do it. Was it Francis and Deering or Deering and Francis? Oh, sorry. This is from Francis, Lau, and Ratliff. So this neighborhoods, etc., That's the paper where they come from. So you might want to take a look at them later yourselves. All right, so here's the proof of the corollary. So I have two applications, one outputting NAR, the other one outputting A cap, R cap neighborhood. And I'm just assuming without loss of generality that R is less than or equal to R cap. There's no loss of generality in that assumption. Okay, so we have NAR equals NA cap R cap, which is the entire intersection. Now, so I'm going to apply the algorithm a third time, this time with every radius reduced by epsilon, where epsilon is precisely the smallest, the smaller of the radii, the R, okay? So when you do that, the output will be, what will it be? It will be NAR minus epsilon, which gives you 0 for the radius. Of course, we applied it in the same order as in the first application. Okay, maybe I should state that. Apply now SIP in the same order as in the first application, but this time with reduced radii. Okay, so the output will be this, which is equal to how much? A. It's the singleton point A. Okay. Do the same for application number 2 to get N A cap R cap minus epsilon, which is going to be whatever it is. What will it be? The second application, when you apply SIP a fourth time, this time in the same order as application number 2, you get the same point A cap. The radius will be reduced by epsilon again. Okay? Well, since the two applications use the same radii, then we must have this relationship, okay? Because we're using the same data again. Since the left side is equal to the singleton A, then of course we have an A cap, R cap minus epsilon. This neighborhood is the singleton A. Clearly then, this implies, what does it imply? Well, first of all, R cap minus epsilon is a non-negative number because of our assumption. Number two, if it's not a singleton, it will have other points in it, so this relationship will not hold. So it has to be a singleton. But if it's a singleton, it cannot be any different from what you have here. Clearly, this implies A cap is A, which also implies, because it's a singleton, R cap is also equal to, that's 0. R cap minus epsilon is equal to 0, which implies R cap is equal to R. Okay?